Alright, now we've got to do some pretty heavy and abstract linear algebra. So before we do it, let me just note that as far as I'm concerned, basics of linear algebra in 19th century were developed with the main motivating application to the theory of differential equations. It kind of was the big purpose, and this is probably one of the first examples of a very common situation in mathematics when an abstract theory, in this case linear algebra, helps to solve some very, very practical question. So in this case, the theory of differential equations is considered to be practical because differential equations, they model a lot of phenomena in real life and especially in physics. Alright, so the first theorem that I'm not going to even to prove because it is abstract, but it's very, very simple. So the proof here is just you take this, you take this, and then you substitute, from here you compute y prime, y double prime, and then you just substitute this into the differential equation, and you see that you get a true equality. So the proof here is very, very simple. But we already saw how it works on specific examples, so I hope it's alright if I skip the proof. But what it essentially says is that that all solutions of a homogeneous linear differential equation form a vector space. So notice that it doesn't have to be a second order differential equation actually. So a linear differential equation of any order, if the right hand side is 0, then all its solutions form a vector space. Alright, then the structure theorem tells us that if we have any two linearly independent solutions, some specific linearly independent solutions, like, remember that in the case when the equation was y double prime minus y equals 0, then the two linearly independent solutions were y1 equals e to the t, y2 equals e to the minus t. Then every solution is going to be a linear combination of these two linearly independent. So, in other words, in linear algebra terms, this theorem just tells us that the dimension of the solution space is 2. So, for example, now we can rigorously conclude that there is no more solution of this differential equation, that every solution can be presented in the form e to the rt plus some constant times e to the t plus some other constant times e to the minus t. So there is nothing else. So this is what's important. So and nothing else. All right. Now we're going to prove this theorem. So it is a bit abstract, but I hope it's all right. So first of all, notice that every solution of the, so what we know is that all solutions of this differential equation, they form a vector space. And of course, any solution is going to solve some initial value problem, right? So example, if say our our differential equation is y double prime minus y is 0, and suppose that we wrote a particular solution, so like 3 e to the t minus e to the minus t. So this is our y some specific solution, and suppose that the initial value of t is, say, I don't know, 27, right? Then y prime is going to be 3 e to the t plus e to the minus t, and it means that our y solves the initial value problem with the initial condition y of 27 is 3 to the times e to the 27 minus e to the minus 27, and y prime of 27 equals 3 e to the 27 plus e to the minus 27. Right? Now, let us construct a linear transformation from the space of solutions of our differential equation to the two-dimensional coordinate space. So, for example, again, in our simple example, y double prime minus y is 0. So suppose that my t is, for example, t0 is 0.5. Then my a sends every y to the corresponding pair of numbers, so which is y of 0.25 and y prime of 0.5. For example, a of, say, 2 e to the t plus e to the minus t would be the following vector. The first entry is going to be the value of this function at 0.5, so which is 2e to the power 0.5 plus e to the minus 0.5, and the second entry is going to be the derivative evaluated at the point 0.5, so which is, sorry, not is going to be 2 again, 2 e to the 0.5, sorry about this, minus e to the minus 0.5. Alright, so the point is that this linear transformation is an isomorphism. So first it is onto because of the existence part of the existence and uniqueness theorem, right? Since every initial value problem has a solution, it means that for every, in terms of this notation, it means that if I give you any vector from R2, then there is a solution with such an initial condition. So that's why this linear transformation is onto. But at the same time, it is one-to-one because of the uniqueness part, right? So there is only a unique solution, and hence it is one-to-one. But since it is onto and one-to-one, it must be an isomorphism, and therefore the dimension of these two.